Hello. In this video I will show how to calculate the electric field inside a thin film using a simple example. We will also see how this helps us to understand optical coatings and anti-reflection effects. This video will be quite technical. We will consider a simple three-layer system with real refractive indices N1, N2 and N3. A plane wave is incident from medium 1 and we assume its amplitude is normalized to 1. The thickness of the thin film is d. The Fresnel reflection and transmission coefficients between media I and j, when they are isolated, is defined as follows. They represent the ratio of the corresponding electric field amplitudes. Now let's write down the electric field expressions in all three regions. In region 1, the field is the sum of the incident and reflected waves. In region 2, the field consists of two counter-propagating waves inside the thin film. And in region 3, there is only the transmitted wave. To find the coefficients R, D, and T, let's consider what happens step by step. A wave is incident from medium 1. It is partially reflected at the first interface with reflection coefficient R12. The rest of the wave is transmitted with transmission coefficient T12 and then it travels through the film, acquiring a phase factor E in power E delta, where delta equals 2p and 2d over lambda. At the second interface, part of the wave is reflected with coefficient R23. This reflected part travels back through the film, acquiring the same phase factor again, and is partially transmitted into medium 1 with transmission coefficient T21. But this wave is partially reflected again from the first interface, and the same path again. If we look carefully at the resulting formula, we see that every next term will be multiplied by q. After all, we see that it is a geometric progression with the sum equals to the following expression. After some additional computations, we get the final expression. Using the same procedure, we can now find the coefficient d, which gives the field inside the thin film. This computation is actually simpler. All additional reflections happen entirely within the film, and the multiplication factor for each round trip forms a geometric series. The common ratio of this series always has the following form. Note that all the backward traveling waves elevated at position 0 are just the forward traveling wave multiplied by the same factor. This makes it easy to write the expression for d', the amplitude of the backward wave inside the film. Then d' equals d multiplied by e in power e delta multiplied by R23 and again by e in power e delta. To find the transmitted field and the transmission amplitude t, we now evaluate everything at position d. Thus, on the left-hand side, we must include the exponential factor e in power e k3d to account for the phase of the wave in medium 3. The resultant transmitted field is simply d multiplied by t to 3 multiplied by exponent. This gives us the final expression for the transmission amplitude. Note that these were amplitude coefficients. To find the transmission coefficient in terms of intensity, we use the relation between intensity and electric field amplitude and normalize everything by the incident intensity. This leads to the following expressions. In general, this kind of coating can be used in many applications, for example in lenses, solar panels, or display screens to reduce unwanted reflections. Hi! Creating these videos requires a lot of time and effort. If you find them even slightly helpful, your feedback and support especially subscribing, really helped me to keep going. Now suppose we have two materials with refractive indexes N1 and N3, and we want to add a thin film with index N2 such that at a specific wavelength, say 550 nanometers, the reflection becomes zero. We want anti-reflection coating. Let's take the formula for total reflection coefficient and set it equal to zero. If all coefficients are real, we find that the condition absolute value of R12 equals absolute value of R23 must hold. Expanding the expressions for the Fresnel coefficients gives us two possibilities, either n1 equals n3 or n2 squared equals n1 multiplied by n3. This second case gives us a non-trivial solution for the ideal anti-reflection coating. As for the phase condition, to make the two reflected waves cancel out, we need the optical thickness of the film to satisfy d equals lambda over 4 and 2. This corresponds to a destructive interference at the target wavelengths. Let's take a visual look at this. First, we will plot how the reflection and transmission coefficients depend on the thickness of the film. The result might loosely resemble diffraction from a grating with an infinite number of slits, and in fact, that's not far off. A thin film essentially produces interference from an infinite number of internal reflections. Now let's look at the dependence on wavelengths. We will also check the anti-reflection condition. As we can see, when we plug in the right values for the refractive indices, the reflection minimum appears exactly at the target wavelengths. Thank you for watching. I hope this video was useful for you. Bye!